Tonight, you are going to find out that the fastest thing in the universe is not fast enough to matter, not fast enough to cross the distances that separate stars from each other, not fast enough to let a civilization reach another one before thousands of generations have lived and died on the ship, not fast enough to outrun the expansion of space itself, which is quietly sealing off entire regions of the universe from us permanently with no door left open. 299 down, 792 kilometers per second. That number is real. Every experiment we have ever run confirms it. And when you place it next to the actual size of the universe, it starts to look less like a speed and more like a sentence. Tonight, we follow that sentence to its end. The energy it costs to even approach the speed of light. What relativity does to time on the journey. Why some parts of the universe are already gone, not far gone, and why the silence from the rest of the cosmos might not be a mystery at all. If you find these slow cosmic walks useful before sleep, a quiet like or subscribe means a lot. We begin. There is a particular kind of knowledge that lives in your head but never reaches your body. You know it. You can say it. You could write it on a piece of paper and hand it to a stranger, and they would probably recognize it immediately. But you have never actually felt it, not the way you feel the weight of something you are holding, or the cold of a window on a winter night, or the resistance of water when you push through it. The number just sits there, behind your eyes, waiting for something to give it meaning. 299, 792 kilometers per second. That is the speed of light. That is how fast a photon, a single packet of light, travels through empty space. And almost everyone who has passed through a science class at any point in their life has encountered that number. It is one of the most printed numbers in the history of textbooks. It appears on posters, in documentaries, in the opening slides of physics presentations around the world. People hear it and nod, of course. The speed of light. 299,992 kilometers per second. Fast. But knowing a number is not the same as understanding what it means. And the distance between those two things, between knowing and actually feeling, is where this entire conversation lives. So let's start small. Let's start with something you can feel. The distance between your eyes and the screen you are looking at right now is probably somewhere between 30 and 60 centimeters. If you were to measure the time it takes light to cross that gap, from the screen to your eyes, you would get a number so small it has no practical meaning in human terms. Something on the order of 1/billionth of a second, less than the time it takes a single neuron in your brain to fire a signal. The light arrives before your nervous system has the capacity to register that it wanted to receive it in the first place. You see the screen essentially the moment the light leaves it. That is what fast feels like when distances are small. Now extend the distance. The moon is roughly 384,400 kilometers from Earth. That is a real distance. Far enough that driving a car at highway speed without stopping would take you about 5.5 months to get there, if such a road existed, but light crosses that gap in about 1.3 seconds. A little over 1 second. You could sit in a room, aim a laser at the moon, and in the time it takes you to draw one complete breath, the light would arrive at the lunar surface and the reflected light would be almost halfway back to you. Still fast. Still within the range of something the mind can hold. Now go further. The sun is approximately 150 million kilometers away. Light takes about 8 minutes and 20 seconds to travel from the sun's surface to your window. This measurement, this travel time, defines what astronomers call one astronomical unit, the base unit of distance within our solar system. 8 minutes and 20 seconds. That is how long it takes for the energy that will heat your face tomorrow morning to complete its journey from where it was generated by nuclear fusion to the window it passes through. And here, without yet going anywhere unusual, something starts to shift. Because 8 minutes means something. 8 minutes is a real interval of time, long enough to make a cup of tea, long enough to walk a few city blocks, long enough for a short conversation to begin and end. 8 minutes means that the sun you see right now, the image of it, the light carrying that image, left its source before you started reading this sentence. If the sun were to silently and completely vanish this second, you would not know for 8 minutes. You would feel its warmth on your skin. You would see its light in the sky. The birds outside would not change their behavior, and the sun would already be gone. That is not a thought experiment designed to be clever. That is how light works. That is what a finite speed means, applied to real distances. Now we go further still. Pluto, at its farthest point from the Sun, is about 7.4 billion kilometers away. Light takes approximately 5 hours to cross that gap. If you sent a radio signal, which also travels at the speed of light, to a probe sitting in the outer solar system near Pluto, you would wait over 6 hours for the signal to arrive, and another 6 hours for any response to return. The engineers who managed the New Horizons mission, the spacecraft that flew past Pluto in 2015, dealt with exactly this. Every command sent from Earth arrived hours later. Every piece of data the spacecraft sent back took hours to reach the receivers. The spacecraft was, during its closest approach to Pluto, entirely on its own, executing a pre-programmed sequence because there was no way to react in real time across a distance that light itself takes half a day to cross. And Pluto is still inside our solar system. It is still within the gravitational neighborhood of our own Sun, the edge of the Oort cloud, the vast diffuse shell of icy bodies thought to represent the outermost boundary of the Sun's influence. Extends perhaps 1 to 2 light years in every direction, 1 to 2 years at the speed of light. That is the radius of our solar system in its fullest sense, 299,792 kilometers per second. You knew the number before tonight. What changes tonight is what it starts to feel like when it meets the actual architecture of the universe. Fast is not a property that exists on its own. It only means something in comparison to the distances it has to cross. And the distances ahead of us are about to become very hard to sit with. The Sun you see is not the Sun that exists. Sit with that for a moment. Not the implications yet, just the fact itself. When you look at the Sun on a clear afternoon, through the clouds and the shimmer off a wet road, in the reflection on still water, you are looking at light that left the Sun's surface approximately 8 minutes and 20 seconds ago. The image your eyes receive is not a live broadcast. It is a recording taken automatically by physics, transmitted at the speed of light, delivered 8 minutes late. The Sun you are seeing right now was the Sun as it was just over 8 minutes ago. The Sun that exists at this moment, whatever it is doing, whatever activity is occurring on its surface, has not yet been seen by anyone on Earth. That information is still traveling toward us. This is the nature of a finite speed universe. There is a built-in delay between the moment something happens and the moment it can be observed. For the Sun, that delay is 8 minutes. For the Moon, it is 3 seconds. For the screen in front of you, it is a billionth of a second, so small as to be meaningless in any practical context. But the delay is always there. There is no such thing as truly instantaneous observation across any non-zero distance. There is only observation delayed by varying amounts of time depending on how far away the source is. Physicists call this look-back time. It is not a poetic metaphor. It is a technical term describing a real physical constraint. When you observe any object in space, you are observing it not as it is now, but as it was when the light you are receiving left it. The farther the object, the older the image. The light from Proxima Centauri, our nearest stellar neighbor, takes 424 years to reach us. The light from the center of our galaxy takes roughly 26,000 years. The light from the Andromeda galaxy, that faint smear sometimes visible to the naked eye on a very dark night, takes approximately 537 million years. What you see when you look at Andromeda is not Andromeda. It is a memory of Andromeda from a time before anatomically modern humans walked on Earth. The concept sounds abstract until it connects to something concrete. Consider that some of the stars you can see in the night sky, specific individual stars you might point to, may no longer exist. A star 600 light-years away that you observed tonight existed 600 years ago, and the light carrying that observation has been in transit ever since. Whether that star is still there, still burning, is information that has not yet reached you. If it exploded 4 centuries ago, the news is still in transit. In 2 centuries or 3, a bright new point of light will appear in the sky, the supernova, and it will be news of something that has already been over for hundreds of years by the time anyone on Earth sees it. You can look at a dead star. You can observe something that does not exist, not as a figure of speech. as a direct, literal consequence of how light moves through space. This has transformed how astronomers think about what they do. When the James Webb Space Telescope captures light from galaxies 13 billion light-years away, it is receiving light that began its journey 13 billion years ago, when the universe was less than a billion years old, and the galaxies being observed were in their earliest stages of formation. JWST is not a telescope so much as it is a time machine pointed backward. The further you look in space, the earlier the era you are examining. The universe provides, through this built-in delay, a complete archive of its own history. Every layer of distance corresponds to a layer of time. The whole cosmic story, from almost the beginning to nearly the present, is encoded in the light surrounding us. We are immersed in a historical record that requires no excavation, just instruments sensitive enough to read it. But here is the other side of what this means. If you wanted to see the universe as it actually is, not as it was, but as it currently is, at this moment, you would need information that travels faster than light. You would need signals that cross cosmic distances instantaneously. And we have established that no such signals exist. No information moves faster than light, which means the present state of the universe, its actual right now configuration, is permanently inaccessible to us. We can never see the universe as it is, only as it was. The current moment is local. It cannot be shared across cosmic distances. There is no universal now. Two observers separated by millions of light-years cannot even agree in the framework of relativity on which events are simultaneous and which are not. Simultaneity, like so much else, turns out to be observer-dependent, a fact that falls out naturally from Einstein's work. We are inside a universe that keeps perfect records of its past and hides its present completely. That is the deeper meaning of 8 minutes, not just a delay. A fundamental separation between observation and reality that grows with every kilometer of distance, and at the distances between stars, between galaxies, between the structures that make up the large-scale universe, that separation becomes total. There is a second consequence of look-back time that is easy to miss. Not only are we unable to see the universe as it currently is, we are also unable to affect it in real time. When astronomers observe a galaxy undergoing a cataclysm, a supermassive black hole devouring stars at its center, a galaxy cluster colliding with another, they are watching events that happened millions of years ago. There is no intervention possible. There is not even any point at which intervention would have been possible within any reasonable human timescale. By the time the light from such an event reaches us, the event has long since resolved into whatever it resolved into, completely beyond any influence from anything on Earth. This asymmetry, that we can observe the past but cannot influence it, is familiar from everyday experience at short ranges, where the delay is negligible, but at cosmic distances it becomes total. The universe presents us with an enormous, detailed, magnificent record of its past, and hides its present completely. We are archaeologists by necessity. We cannot be anything else. This is worth sitting with, not as a source of frustration, but as a genuine feature of the situation. The universe is not hiding its present from us out of indifference or design. It is the inevitable consequence of having a finite speed of information transfer in a very large space. If the speed of light were 10 times faster, the delay would still exist, only shorter. The structure is fundamental. The only way to know the present state of a distant object would be to be there. And being there, as this entire conversation has been about, is not an option available at any useful speed. What astronomers have learned to do with look-back time is treat it as a scientific resource rather than a limitation. Because the universe comes preloaded with observations from different eras, it is possible to study cosmic evolution directly, to look at what galaxies looked like 1 billion years after the Big Bang, 3 billion years after, 7 billion years after, and compare them with galaxies we see nearby, which represent the universe as it is relatively recently. The archive is complete. Every moment of cosmic history, from the earliest structures to the present, is encoded in the light surrounding us. This is how we know that early galaxies looked different from present-day ones, how we know that the rate of star formation across the universe has declined over time, how we know the large-scale structure of the universe, the vast filaments and voids that connect galaxy clusters, assembled gradually from smaller seeds. All of this knowledge comes from reading different layers of look-back time, comparing different depths of the archive. The delay that feels like a limitation is, from another angle, the feature that makes cosmic science possible. For most of human history, light was assumed to be instantaneous. This was not, as it might seem from this distance, a failure of intelligence. It was a failure of scale, the most understandable kind. Every distance available for testing in daily experience was too small to reveal any detectable delay. The light crossing a room, a field, even a city, arrived so quickly that no instrument built from wood and metal and human hands could register any gap between emission and receipt. You opened your eyes and the world was simply there. The fire was lit and the light was already everywhere in the room before you could begin to measure it. Aristotle argued that light was instantaneous. René Descartes, writing in the 17th century, constructed philosophical arguments for the same position. He believed that light propagated as a pressure through a medium, and that this propagation was necessarily instantaneous. Even Galileo, who was not a person inclined to accept things he could test, attempted a measurement. He stationed 2 assistants on hilltops a few kilometers apart, each with a lantern, with instructions to uncover their lantern the moment they saw the other's flash. He found no detectable delay, which was correct. The delay across a few kilometers of air is around 10 millionths of a second. Human reaction time is hundreds of times slower. The signal was completely buried in noise. The first real evidence came not from a laboratory experiment, but from watching a moon of Jupiter. In the early 1670s, a Danish astronomer named Ole Rømer was working at the Paris Observatory under the patronage of the French royal court. His assigned task was practical: produce precise tables of the orbital periods of Io, the innermost of Jupiter's 4 large moons, so that the tables could be used by sailors to determine longitude at sea. Io orbits Jupiter in approximately 42.5 hours. Because its orbit is very nearly edge-on when viewed from Earth, it regularly passes into Jupiter's shadow and disappears, then reappears on the far side. These eclipses happen with reliable regularity and are observable with a modest telescope. Rømer observed them carefully. He recorded timestamps. He built a detailed record of when Io's eclipses were predicted to occur and when they actually occurred. And he noticed something that the predictions could not explain. When Earth was on the same side of its orbit as Jupiter, closer to the giant planet, the eclipses of Io arrived slightly early relative to the predicted schedule. When Earth had moved to the far side of its orbit, at maximum distance from Jupiter, the eclipses arrived late. The discrepancy accumulated to approximately 22 minutes over the course of 6 months, as Earth moved from its nearest point to Jupiter to its farthest. Rømer's interpretation was careful and correct. The delay was caused by the finite travel time of light. When Earth was farther from Jupiter, the light from Io's eclipses had to cross more space before reaching the observatories, extra distance equal to the diameter of Earth's orbit. This extra distance took time for light to cross, and that time showed up as a systematic delay in the observations. He used his records to estimate the speed of light. His figure was approximately 220,000 kilometers per second. The actual value was 299,572. Rømer was off by about 26%, due primarily to inaccurate knowledge of the distances involved. But the method was valid. The conclusion was valid. Light was not infinite. It traveled at a finite speed, and that speed was, for the first time in history, approximately known. This was 1676. Confirmation came from a different method in 1728. The British astronomer James Bradley, working to measure precise stellar positions, noticed that stars appeared to shift their positions over the course of a year in a way that could not be explained by parallax. The expected positional shift due to Earth's changing location in its orbit. Instead, the observed shift was perpendicular to what parallax would predict, and its magnitude matched the ratio of Earth's orbital speed to the speed of light. The phenomenon is called stellar aberration. Because Earth is moving through space, the light from stars arrives at a slight angle relative to the direction the telescope is pointing. Just as rain falls at an angle relative to a stationary vertical umbrella when you run through it, Bradley calculated a speed of light of approximately 301,000 kilometers per second, within 1% of the correct value. By the mid-18th century, it was beyond question. Light moved. It traveled through space. It took time. And with that established, the night sky was never quite the same again. Because if light takes time, if every observation carries a delay, then everything seen in the sky is a message from the past sent at a speed that, remarkable as it is, cannot change the fact that enormous distances introduce enormous delays. The stars you see on a clear night are not a view of the current universe. They are a collection of dispatches from different eras, all arriving at the same moment, from sources separated by hundreds or thousands of light years. The night sky is not a window. It is a mailbox, and Rømer found the first proof of that, watching a small moon disappear behind a planet with nothing more than a telescope and a calendar, and the patience to notice that the numbers did not quite add up. The story of measuring the speed of light continues past Bradley through increasingly precise experiments over the following 2 centuries. In 1849, the French physicist Hippolyte Fizeau performed the first purely terrestrial measurement of the speed of light. He used a rapidly spinning toothed wheel and a distant mirror. Light passed through a gap in the wheel, travelled 6 kilometers to the mirror, reflected back, and either passed through a gap again or was blocked by a tooth that had rotated into place during the travel time. By measuring the wheel speed at which the returned light was blocked and then unblocked, Fizeau obtained approximately 313,000 kilometers per second. In 1862, Léon Foucault improved the approach using a rotating mirror and obtained 298,000 kilometers per second within 1% of the correct value. Albert Michelson spent much of his career refining the measurement, eventually earning the Nobel Prize in Physics in 1907. His measurements through a vacuum tube in the 1920s approached the precision that modern methods would later confirm. The current accepted value, 299.50 het meters 790.58 meters per second exactly, was established not by measurement but by definition. In 1983, the International Bureau of Weights and Measures redefined the meter to be the distance light travels in exactly 1,792,790,458 of a second. The speed of light became a defined constant, and the meter became derivative from it. This definitional choice reflects a deep physical reality. The speed of light is not an experimental result that could, in principle, be wrong and require revision. It is a fundamental constant of nature built into the structure of space-time. Fixing its numerical value exactly is simply acknowledging what it is. 300 years of measurement, from Rømer watching Jupiter, to Bradley tracking stellar aberration, to Fizeau spinning a wheel, to Michelson polishing mirrors, to the 1983 redefinition, all converging on the same number. The universe is consistent about how fast its own logic propagates. Proxima Centauri. That name appears in almost every conversation about interstellar space, and for understandable reasons. It is our nearest stellar neighbor, the closest star to Earth other than our own Sun. The target most often cited when people imagine humanity's first serious attempt at another solar system. It is 424 light-years away. That phrase 4.24 light-years away. That phrase 4.24 light-years is presented in textbooks and documentaries as though it conveys something, as though 4 years at the speed of light gives the mind a proper grip on the distance. You can picture 4 years. You have lived through many of them. 4 years is a presidential term, a university degree, a significant portion of a child's development. 4 years seems manageable. What the phrase seems manageable, what the phrase conceals, is what 4.24 light-years translates to in units the body can relate to. 4.24 light-years is approximately 40 trillion kilometers. Written numerically, 40,000, 40,000 billion, 40,000 billion. If you drove a car at 100 kilometers per hour, a reasonable highway speed without stopping for fuel, for food, for sleep, for any reason whatsoever, it would take roughly 46 million years to arrive. The earliest known fossils of organisms with hard shells appear in the geological record approximately 540 million years ago. You would reach Proxima Centauri before complex animal life had even begun on Earth. if you had started driving when the first simple animals evolved. That is our nearest neighbor. The word nearest is carrying an extraordinary amount of weight in that description. It implies a kind of proximity. That of all the options, this one is manageable. That it represents the more accessible end of a spectrum. And in the context of the galaxy, it is. The galaxy is 100,000 light-years across. 24 light-years is almost nothing on that scale. But in the context of anything humanity has ever physically reached, it is not close by any stretch of the meaning of that word. To send a radio signal to Proxima Centauri, a signal that travels at the speed of light itself, the maximum possible speed for any information transfer, takes 24 years one way. To receive a reply, assuming something at the other end received the signal and responded immediately, takes another 24 years. The minimum round-trip communication time with our nearest stellar neighbor is 48 years. You would send a message today, and the earliest possible response would arrive when a newborn child is finishing primary school. That is the best-case communication scenario. Not a face-to-face meeting. Not a shared meal. Not a conversation of any kind that would feel recognizable as a conversation. Just a message and a reply across the most optimistic possible channel, taking the better part of a decade. Astronomers discovered in 2016 that Proxima Centauri appears to host a planet in the rough vicinity of what is called the habitable zone, the range of orbital distances where, depending on atmospheric composition and other factors, liquid water might exist on a surface. The planet is called Proxima Centauri b, and its existence was inferred from the small wobble it induces in its host star's motion. A rocky world, roughly Earth-sized, orbiting the nearest star. The discovery generated genuine excitement. If there is a rocky planet around the nearest star, the conversation about what might be out there shifts from purely abstract to potentially specific. But caution is warranted. Proxima Centauri b orbits its star at a distance far closer than Mercury orbits our Sun, because Proxima Centauri is a red dwarf, much smaller, cooler, and dimmer than our Sun. To receive enough energy to potentially support liquid water, the planet has to be very close to its star. That proximity creates its own problems. Red dwarfs are prone to violent stellar flares, intense bursts of ultraviolet radiation and charged particles that can strip planetary atmospheres over geological timescales. Whether Proxima b has retained any atmosphere, whether it has liquid water, whether it has conditions recognizable as hospitable to life as we understand it, we do not know. Models give wildly different answers depending on assumptions about atmospheric composition, magnetic field strength, and the planet's history. What we know with confidence is the distance, 40 trillion kilometers, and across that distance, traveling at the fastest speed the universe permits, a message takes 24 years to arrive. Now consider what it would take not to send a message, but to send something physical, something that could arrive, examine the environment, and perhaps send back what it found. A probe. Unmanned. One way. Voyager 1, our most distant spacecraft, has been traveling for nearly 50 years and covered roughly 24 billion kilometers. The distance to Proxima Centauri is 40 trillion kilometers. Voyager 1, moving at approximately 17 kilometers per second, would take roughly 73,000 years to cover that distance, if it were aimed at Proxima Centauri, which it is not. 73,000 years. All of recorded human history, writing, agriculture, cities, philosophy, mathematics, science, every text ever preserved spans roughly 5,000 years. Reaching the nearest star with the technology we currently have would require a journey nearly 15 times longer than the entire recorded human story. This is not a reason for despair. It is a calibration. It is the universe demonstrating, clearly and precisely, what the actual numbers look like. And the actual numbers require a completely different category of thinking if we are to make any progress across these distances. What that thinking looks like is where we go next. The communication problem, considered on its own terms, reveals something that most discussions of contact with extraterrestrial intelligence underestimate. Suppose a signal of unambiguous artificial origin were detected from the direction of Proxima Centauri. A structured sequence, clearly not producible by natural processes, clearly mathematical, clearly intentional. The answer to the most fundamental question in the search for extraterrestrial intelligence. That signal left its source 24 years ago. Any response sent from Earth would take 24 years to arrive. The reply to that would take another 24 years to return. A single question and answer exchange takes 48 years, minimum, assuming we can formulate a response the moment we receive the signal. A sustained conversation, the kind that allows two parties to build shared understanding, to ask follow-up questions, to explain concepts that require clarification, would unfold across decades. A 10-round exchange would take nearly 90 years. The people who sent the first message might not live to receive the 10th reply, and this is Proxima Centauri, our nearest neighbor. For a star 100 light-years away, the minimum round-trip message time is 200 years. For a star 1,000 light-years away, 2,000 years. For the far side of the galaxy, 200,000 years. The universe has, in effect, designed a situation in which civilizations can announce their existence to each other but cannot converse. They can send dispatches. They cannot have dialogue. The delay makes dialogue impossible across any distance that matters astronomically. Even confirmation that a message has been received and understood would take years or centuries to arrive. This is not a reason to stop searching for signals. A confirmed message, even without a reply, would be profoundly significant. But it changes what contact would mean. Not a conversation. Not a relationship. A piece of mail, years old by the time it arrives, from a civilization that has continued to change during every year of its transit. In September 1977, NASA launched a spacecraft that was not designed to go to the stars. Voyager 1 was built to study Jupiter and Saturn and the moons around them. It carried cameras, magnetometers, plasma wave detectors, and other instruments designed for a multi-year planetary reconnaissance mission. Its expected useful life was measured in years, not decades. The fact that it is still operating, still transmitting, nearly 50 years after launch, was not part of any original plan. But it was launched outward. It received gravity assists close flybys of Jupiter in 1979 and Saturn in 1980 that flung it further and faster than its engines alone could have managed. These assists work by allowing the spacecraft to swing through a planetary gravity field and effectively steal a tiny fraction of the planet's orbital momentum. Jupiter is enormously massive. The fraction stolen is negligible to the planet and significant to the spacecraft. After the Saturn flyby, Voyager 1 was on a trajectory that would carry it out of the solar system entirely. It crossed into what scientists define as interstellar space, the region beyond the Sun's protective magnetic bubble, the heliosphere, in 2012. The confirmation came from instruments detecting a sudden increase in cosmic ray density and a corresponding drop in solar wind particles. Voyager 1 was, unambiguously, in the space between the stars. The first human-made object to be there. As of the most recent tracking data, it is approximately 24 billion kilometers from Earth. The signal from Voyager 1 takes about 22 hours to reach us, traveling at the speed of light. When engineers send a command, they wait 44 hours for the round-trip confirmation. The spacecraft is operated largely on pre-programmed sequences, with commands sent for known upcoming events, because real-time control is simply not possible across that distance. The spacecraft is moving at approximately 17 kilometers per second relative to the Sun. This is faster than almost anything else humanity has launched that sustains its speed over decades. It is the product of careful trajectory design, fuel burn, and gravity assists accumulated over decades of travel. 17 kilometers per second. In 1 hour, Voyager 1 travels 62 Cessna 200 kilometers. In 1 day, roughly 1.47 million kilometers. In 1 year, about 537 million kilometers. The distance to Proxima Centauri is approximately 40 trillion kilometers. At Voyager 1's current speed, the journey would take roughly 74,000 years. Not that it is headed that direction, it is aimed toward a different region of the sky entirely. But even as a thought experiment, the arithmetic is instructive. 74,000 years ago, modern humans were living in small bands across Africa and the Levant. Homo neanderthalensis still walked parts of Europe. Cave paintings were at least 10,000 years in the future. No written language, no agriculture, no cities, no metal tools. Every human tradition, every language, every cultural practice, every scientific discovery, every piece of music ever composed, none of it existed. The world that would eventually produce Voyager 1 was 74,000 years away. That is how long Voyager 1 would take at its current speed to reach the nearest star. New Horizons, the spacecraft that flew past Pluto in 2015 and is now the fifth most distant human object from Earth, was launched with greater initial velocity. It is the fastest spacecraft ever to leave Earth at launch, but it did not receive the same chain of gravity assists that gave Voyager 1 its ultimate speed. New Horizons is currently traveling at roughly 14 kilometers per second. It would take even longer to reach Proxima Centauri than Voyager 1 would. The Parker Solar Probe, designed to study the Sun at extremely close range, reaches speeds of over 170 kilometers per second during its closest solar approaches, faster than anything we have ever measured a human-made object traveling. But it is in a highly elliptical orbit around the Sun, not escaping the solar system. Its high speed is momentary, achieved through gravitational attraction toward the Sun during perihelion passes, and it does not represent a sustained velocity that could be used for interstellar travel. These are our fastest machines. After more than 60 years of spaceflight, these are the records we hold, and none of them could reach the nearest star within 10 human lifetimes, let alone one. This is the universe's way of communicating something simple, that the gap between within the solar system and between the stars is not a gradual continuum. It is a categorical difference. The engineering that works for planetary missions does not scale. The physics of getting between stars requires something fundamentally different in kind, not just in degree. What that something might look like, what serious engineers have actually proposed when they try to close the gap, is worth examining. Because the answers are not nothing. They are real, detailed, and instructive. And they reveal just as clearly as the Voyager numbers do exactly what the universe is asking of anyone who wants to cross its distances. There is a thought experiment worth doing with the Voyager numbers that reframes the problem. Suppose humanity had begun sending Voyager speed probes toward the nearest stars at the very beginning of civilization, roughly 5,000 years ago. Suppose a probe left at the moment writing was first invented in Mesopotamia, moving at 17 kilometers per second. Where would it be today? Approximately 27 trillion kilometers from Earth. That number sounds large. By everyday standards it is. But Proxima Centauri is 40 trillion kilometers away. After 5,000 years of travel, such a probe would have covered about 7% of the distance to the nearest star. It would still have approximately 68,000 years remaining. 5,000 years ago, the wheel had been recently invented. Writing was just beginning. The pyramids of Giza had not yet been built. There were no nation-states, no formal science, no mathematics beyond basic counting. The entirety of what we call human civilization had not yet happened, and a probe launched then, at Voyager speed, would currently be 6.7% of the way to the nearest star. This comparison is not presented to induce despair. It is presented because the numbers make it difficult to think about interstellar travel in human-centric terms. Interstellar space does not scale to human timelines. It does not scale to civilizational timelines. It requires a different category of thinking entirely, one that accepts geological or astronomical timescales as the relevant unit. A civilization committed to Voyager speed colonization of the nearest stars would need institutional continuity spanning tens of thousands of years. No human institution has survived 10,000 years unchanged. The oldest continuous traditions, some religious institutions and legal systems, are a few thousand years old and have changed substantially during that time. The problem of interstellar travel is, at slow speeds, as much a problem of civilizational continuity as it is of propulsion. The universe has arranged things such that the interesting targets require commitments. No civilization has demonstrated the ability to maintain. In 1973, a group of engineers and scientists associated with the British Interplanetary Society sat down to work on a problem that most of their colleagues considered science fiction. The question was whether it was possible, using physics as it actually works and engineering that could plausibly be developed over the following century or two, to design a spacecraft capable of reaching another star system within a human lifetime. Not a generation ship, not a hypothetical vessel requiring unobtainable energy. A real probe, unmanned, one way, that could cross interstellar space and send back scientific data before the people who built it had grown old. The project was named Daedalus, after the Greek craftsman who built wings of feathers and wax. It ran for 5 years, involving dozens of engineers contributing voluntary work alongside their professional careers, and it produced a detailed technical design document that remains one of the most thorough analyses of an interstellar mission ever produced. The propulsion system chosen was nuclear pulse fusion, a process in which small compressed pellets of deuterium and helium-3 fuel would be heated to fusion temperatures by high-powered electron beams inside a large magnetic reaction chamber. The resulting explosions, at a rate of 250 per second during the main drive phase, would push the spacecraft forward. The concept draws on proven nuclear physics. The engineering challenge lies in the precision required to ignite pellets at that rate and survive the output. The target was Barnard's star, a dim red dwarf approximately 9 light-years from Earth, the second closest stellar system to our Sun. At a cruise velocity of roughly 12% of the speed of light, the probe would reach Barnard's star in approximately 50 years. Not fast by cosmic standards, but within a single professional career. Within a human life. The people who built the spacecraft might, if they lived long enough, see the data come back. The fuel requirement was the number that gave pause. Approximately 50,000 tons of helium-3 would be needed to power the main drive phase. Helium-3 is a rare isotope. On Earth, it is almost entirely absent, present only in trace amounts from decay of tritium in nuclear warheads. The outer planets, particularly Jupiter, are thought to contain helium-3 in larger quantities within their atmospheres. The Daedalus design contemplated mining operations in the Jovian atmosphere, using balloons or other atmospheric vehicles to skim and process the gas, conducted over decades before the mission could begin. This was not proposed as something achievable soon. It was proposed as a long-term goal, a demonstration that interstellar travel was at least theoretically possible without invoking any physics that does not exist. Every component of the Daedalus design was based on physics we understood. Nothing required magic. A more recent proposal approaches the problem from a completely different direction. In 2016, the Breakthrough Starshot Initiative, announced with involvement from the physicist Stephen Hawking and funded in part by the investor Yuri Milner, proposed sending not a large spacecraft but a fleet of tiny ones. Each probe would weigh a few grams, be roughly the size of a computer chip, and carry miniaturized sensors and communication equipment. These probes would be equipped with a lightweight reflective sail, a light sail, and accelerated by a powerful ground-based laser array. The concept relies on the fact that photons, packets of light, carry momentum. A sufficiently intense beam of laser light, reflected off a suitable sail, exerts a small but real force on the sail. If the laser ray is powerful enough and the sail light enough, the acceleration can be enormous over a short period. The Starshot proposal envisions accelerating the probes to approximately 20% of the speed of light over a period of minutes, using a laser array with a total power output of around 100 gigawatts, roughly equivalent to the entire current electrical generating capacity of the United States. At 20% of the speed of light, the probes would reach the Alpha Centauri system 424 light-years away in approximately 20 years. This is genuinely exciting as a concept. 20 years is a timescale that human institutions can plan around. A probe launched at 20% of the speed of light, reaching Alpha Centauri in 2 decades, then transmitting its findings back across 24 light-years at the speed of light. The data would arrive roughly 24 years at the speed of light. The data would arrive roughly 24 years after launch, within a generation. The people who designed the mission could receive the results. The engineering problems are substantial. Building a 100 gigawatt laser array that can track and maintain focus on a gram-sized sail moving at a significant fraction of the speed of light is an unsolved problem by a wide margin. The probes would need to survive the acceleration which involves enormous G-forces during the laser boost phase, and then operate reliably for 2 decades in interstellar space, a region more hostile and less understood than any environment we have sent spacecraft into. Communication from Alpha Centauri back to Earth at 20% of the speed of light would require transmitters of extraordinary efficiency to overcome the signal dilution across 4 light-years. These are hard problems. Some of them are at the edge of current engineering capability. Some of them are beyond it, but they are engineering problems. The physics is not forbidden. There is no fundamental law that says a gram-sized probe cannot be accelerated to 20% of the speed of light by laser pressure. The concept is grounded in real, verified physics. The Daedalus study and the Starshot proposal represent the two ends of a spectrum. One proposes a large, fully instrumented probe using nuclear fusion. The other proposes tiny, minimalist probes using laser propulsion. Both require capabilities far beyond what we currently have. Both are achievable, in principle, within the framework of physics as we understand it. Neither involves a crew, neither returns, neither reaches a speed greater than 20% of the speed of light. Because beyond 20% of light speed, the problems deepen in a way that is not simply about building larger lasers or more fuel. The problems become physical in a way that no engineering advancement can fully resolve. That is the energy war. And it deserves its own attention. The contrast between Daedalus and Starshot is worth dwelling on for a moment, because it reveals something about how physicists think about the interstellar problem. Daedalus was a mass and power approach. Build something large, power it with nuclear fusion, send it across interstellar space with enough instruments to do serious science at the destination. The probe was designed to be the size of a building, massing tens of thousands of tons, and the energy budget was enormous. The advantage was that such a probe, if it could be built, would arrive with real scientific capability. A full suite of sensors, cameras, communication systems powerful enough to return data across nearly 6 light-years of space. Starshot is a mass minimization approach. Make the probe so small that the energy required to accelerate it becomes, if not manageable, at least within the realm of conceivable engineering. A gram-scale probe requires far less energy to accelerate than a building-scale one. The disadvantage is capability. A gram-scale probe can carry almost nothing in the way of instruments, and transmitting its findings back across 4 light-years with equipment that weighs grams is an open engineering problem. Both approaches are honest about the fundamental constraint. Getting mass to high speed requires energy, and the ratio is brutal. One approach accepts the mass and tries to find the energy. The other minimizes the mass to bring the energy requirement into range. Neither approach has been built. Neither approach is within current engineering reach, but both are grounded in real physics and represent genuine, detailed thinking about what interstellar travel would actually require. They are not science fiction in the sense of being unconnected to physical reality. They are engineering studies constrained by physical reality, and what they reveal about physical reality is unambiguous. Crossing the gap between stars requires capabilities that are, at minimum, a century of technological development beyond where we currently stand. And that is for an unmanned probe. A crewed mission with return journey at speeds fast enough to be survivable remains beyond the horizon of any serious near-term planning. There is a piece of mathematics that governs how much fuel you need to change a spacecraft's velocity by any given amount. It is called the Tsiolkovsky rocket equation. It was derived in 1903 by Konstantin Tsiolkovsky, a Russian schoolteacher who worked in relative obscurity for much of his life and is now recognized as one of the founding theorists of spaceflight. The equation is not complicated in its form. It can be written in a single line, but its implications are severe. The equation says that the amount of propellant required to achieve a given change in velocity grows exponentially with the size of that velocity change relative to the exhaust velocity of the propellant. For slow speeds and efficient propellants, the ratio of fuel to payload is manageable. For high speeds, it becomes crushing, and for speeds approaching a significant fraction of the speed of light, it becomes physically catastrophic in a way that changes the nature of the problem entirely. Consider the most efficient chemical propellant we have, liquid hydrogen and liquid oxygen, used in engines like the Space Shuttle main engine. The exhaust velocity of this combination is about 4 kilometers per second. To accelerate a spacecraft to 1% of the speed of light, just 3,000 kilometers per second. The ratio of fuel to payload required is so large it has no physical meaning. You would need more fuel than exists in the observable universe, loaded into a spacecraft the size of an atom. This is why chemical rockets cannot reach the stars. It is not a matter of scaling up the technology. The math literally forbids it. The equation produces fuel requirements that exceed the mass of solar systems. Move to nuclear propulsion. Fission and fusion offer far higher exhaust velocities. The Daedalus design proposed effective exhaust velocities of around 10,000 kilometers per second. The fuel-to-payload ratios become more tractable, though still extreme. This is why Project Daedalus required 50,000 tons of fuel for a probe with a relatively modest final mass. Now consider antimatter. Antimatter is the theoretical ceiling of reaction-based propulsion. When a particle of ordinary matter meets its antimatter counterpart, both are completely annihilated and converted entirely into energy. According to Einstein's E equals mc squared, the efficiency is 100%. Every gram of antimatter annihilating every gram of matter produces the maximum possible energy from those masses. There is no more efficient fuel source in known physics. To accelerate a spacecraft of 1,000 kilograms, roughly the mass of a small car, which is actually a very modest spacecraft, to 10% of the speed of light using antimatter propulsion, you would need approximately 45,000 kilograms of antimatter, about 45 times the mass of the spacecraft in fuel, which is actually a reasonable ratio by the standards of rocketry. The problem is not the ratio. The problem is the antimatter. The world currently produces antimatter primarily at large particle accelerator facilities, the most capable of which is CERN in Switzerland. CERN can produce approximately 10 nanograms of antiprotons per year, 10 billionths of a gram. At that production rate, accumulating the 45,000 kilograms needed for a single small interstellar probe would take roughly 4.5 quadrillion years. The universe is approximately 8 billion years old. The time required to produce the fuel at current rates exceeds the age of the universe by more than 300,000 times. This is not a budget problem. It is not a political problem. It is a fundamental mismatch between what the physics of interstellar travel demands and what the physics of antimatter production can supply. And the relativistic rocket equation, when you approach higher fractions of the speed of light, becomes even more punishing. At 99% of the speed of light, even with perfect antimatter propulsion, the fuel-to-payload ratio approaches thousands to 1. For a crewed vessel of any practical size, with life support, radiation shielding, food, water, medical equipment, structural integrity for decades of travel, the fuel mass required becomes planetary in scale. There is no cheating the equation. It is derived from conservation of momentum, one of the most fundamental principles in physics. Conservation of momentum is not a guideline, it is a constraint on everything that has ever moved or ever will. The energy wall is made of these numbers. It is not a technological barrier that additional funding or engineering creativity can dissolve. It represents the actual energetic cost that the universe charges for high-speed travel through its own geometry. And the universe, it turns out, charges an amount that grows faster than exponentially as you approach the speed of light. Any civilization attempting interstellar travel faces this wall. Not a version of it, this wall with these specific numbers derived from these specific fundamental constants. The Tsiolkovsky equation, the mass-energy relationship, the conservation of momentum, these are not Earth-specific physics. They are the physics of the universe. A civilization in a galaxy a billion light-years away faces exactly the same equation, with exactly the same implications. The energy required to move mass quickly through space is built into the structure of reality. It cannot be legislated away. It cannot be innovated around unless the innovation involves not moving mass through space at all, and doing something else instead. What that something else might look like is a question we will return to, but first there is another wall. One that Einstein found inside his equations, hidden in the structure of space and time. It is the wall that turns the journey into exile. There is a comparison that puts the antimatter production gap in context in a way the raw numbers alone may not. The total energy output of all human civilization every power plant, every vehicle, every industrial process, every light on every street in every city on Earth runs at approximately 18 terawatts continuously. In 1 year, this amounts to roughly 7 times 10 to the 20th joules. It is what keeps 8 billion people and their entire technological civilization functioning. To produce the antimatter needed for a single 10% light speed interstellar mission, the energy cost would be approximately 4.45 times 10 to the 27th joules, roughly 8 million times the total annual energy output of human civilization. Even if you could redirect the entire energy production of our civilization entirely to antimatter production with perfect efficiency, it would take approximately 8 million years to accumulate the required fuel. The universe charges an enormous toll for modest speed, and 10% of light speed is still, on cosmic terms, very slow. At 10% of the speed of light, crossing the Milky Way takes 1 million years. Reaching Andromeda takes 25 million years. The energy wall does not merely make interstellar travel expensive, it makes any travel at meaningful cosmic speeds essentially impossible within any timescale that would matter to a civilization, given the energy sources available to anything less than a star-harvesting civilization. Some proposals attempt to sidestep the wall by using existing energy rather than generating it. Laser sails, as in the Starshot proposal, push the cost into the laser array, which still requires hundreds of gigawatts of sustained power. There is no free path. Every approach to high-speed interstellar travel carries an energy cost that exceeds current human capability by orders of magnitude. What this implies for any civilization is that interstellar travel, if it happens at all, requires energy infrastructure of a scale that dwarfs current human civilization many times over. And building that infrastructure is itself a project requiring resources and timescales far beyond what any current institution can plan around. The energy wall is not a milestone waiting to be passed with sufficient investment. It is a fundamental feature of the universe that requires civilizational transformation of a kind that is, under the most optimistic assumptions, centuries away. In 1905, a young patent clerk in Bern, Switzerland, published 4 papers in a single year, any one of which would have established a significant scientific reputation. The most famous of the 4 was titled, in translation from German, On the Electrodynamics of Moving Bodies. It ran to about 30 pages. It contained no bibliography and cited no prior work. It was built on 2 postulates. The first, the laws of physics are the same for all observers moving at constant velocity. There is no experiment you can perform inside a sealed, smoothly moving spacecraft with no windows, no way to look outside, that would tell you whether you are moving or sitting still. Motion is relative. There is no universal rest frame. The second, the speed of light in a vacuum is exactly the same for all observers, regardless of the motion of either the light source or the observer receiving the light. The second postulate is where the strangeness begins. Consider the intuition it violates. If you are standing at the side of a road and a car approaches at 100 kilometers per hour, then turns on its headlights, the light from the headlights travels toward you at the speed of light. If the car were moving toward you at half the speed of light, you might expect the light from the headlights to reach you faster. The source is approaching, so the light should be closing the gap more quickly. That is how sound works. That is how everyday wave propagation works. Light does not work this way. No matter how fast the car is moving, toward you, away from you, in any direction, the light it emits reaches you at exactly the same speed, 299,797 kilometers per second. The motion of the source does not add to or subtract from the speed of light. This was confirmed definitively in 1887 by Albert Michelson and Edward Morley, who measured the speed of light in 2 perpendicular directions as Earth moved through its orbit and found exactly 0 difference. The experiment was so precise and its null result so definitive that it was immediately understood to be a fundamental result, not an experimental error. Einstein took the Michelson-Morley result as a given and asked, what must the universe be like if this is true? The answer required revising assumptions so fundamental that they had never been examined. If the speed of light is constant for all observers, then time itself must pass at different rates for observers moving at different speeds. This is not a matter of clock imprecision or experimental artifact. It is a genuine physical phenomenon, as real as mass or charge. The mathematics describing this, formalized in the Lorentz factor, which describes the ratio of time elapsed for a moving observer to time elapsed for a stationary one, produces results that feel counterintuitive but are confirmed to extraordinary precision by experiment. At 10% of the speed of light, a moving clock runs about 0.5% slower than a stationary one. At 50% of the speed of light, it runs about 15% slower. At 90%, it runs at about 44% the rate of a stationary clock. 1 year on a ship moving at 90% of light speed corresponds to 3 years passing at home. At 99%, 1 ship year is 7 Earth years. At 99%, 1 ship year is 22 Earth years. At 99%, 1 ship year corresponds to 71 Earth years. The relationship is not linear for 8 years. The relationship is not linear. It accelerates toward infinity as the ship's speed approaches the speed of light. At the speed of light itself, which is unreachable for any massive object, the Lorentz factor would be infinite. Time would stop entirely for the traveler. This phenomenon was first demonstrated experimentally not in a laboratory but in the upper atmosphere. Cosmic rays, high-energy particles arriving from space, collide with atoms in the upper atmosphere and produce secondary particles, including muons. Muons are unstable. They decay into other particles with a half-life of about 2 microseconds. Given their speed, close to the speed of light, and the distance from the upper atmosphere to the ground, the vast majority of muons should decay before reaching detectors at sea level. The distance is too long for a particle that lives only 2 microseconds, even at near light speed, but they do reach the ground in large numbers because from the muon's reference frame, from the frame of a particle moving at 99+% of the speed of light, time passes much more slowly than it does in the laboratory frame. The muon experiences only a fraction of the elapsed time. Its internal clock runs slow. It decays, but in what from our perspective is much more than 2 microseconds of external time. Time dilation is not a theory. It is a measured fact confirmed every second in detectors around the world and in the GPS satellite system, whose clocks are corrected for it daily. Now apply this to interstellar travel. A spacecraft traveling at 99% of the speed of light toward Proxima Centauri would, from Earth's perspective, take about 3 years to arrive. But from the crew's perspective, due to time dilation, the journey would pass in about 7 months. The crew ages 7 months. Earth ages 4. 3 years. Both are correct in their own reference frame. Neither is wrong. This seems like a gift. And it is, in a narrow sense. It means that even journeys of decades of Earth time might be survivable for the crew. A sufficiently fast ship could carry a crew to a star 100 light-years away in less than 5 years of subjective time, even though a century passes on Earth. The crew is not preserved in suspended animation or frozen. They are simply living in a reference frame where time passes slower. But the cost attached to this gift is one that any civilization would have to confront before building the ship. The crew who left, in what subjective time, arrives to find a civilization that is a century older. Everyone they knew is dead. The children of the people who waved them goodbye are old. The technology has changed. The political landscape has changed. The cultural context in which the mission was conceived may be entirely gone. The crew left as explorers with a mandate from a living civilization and arrived as time travelers to a future that did not plan for their return. This is the exile problem, and it does not improve with faster travel. At 99.9% of the speed of light, the subjective time gets shorter, but the gap between ship time and home time gets larger. A crew traveling at 99.9% of light speed to a star 1,000 light-years away experiences less than 45 years of travel, a single professional lifetime. But 1,000 years pass on Earth. A civilization that sent them out in the 21st century would receive their signal back in the 31st. No one alive at launch would be alive at contact. The universe offers a bargain. You can go far in less personal time, but it costs you your place in history. You depart from one civilization and arrive irreversibly into a future one. The faster you go, the steeper that tray becomes. Any civilization that builds an interstellar ship must reckon with this. Not just the engineering, not just the fuel. The fact that the crew who boards the ship will never return to the civilization that built it. And the universe has still not finished. Everything discussed so far has assumed a universe with fixed geometry. Stars at fixed positions, distances that are large but at least constant. You calculate the gap, you calculate how long light takes to cross it, you decide what speed you need, you assess the fuel cost. The answer might be severe, but at least the problem is stable. The target is where you aimed. The universe does not have fixed geometry. In 1929, after years of careful observation at the Mount Wilson Observatory in California, the American astronomer Edwin Hubble published what became one of the most consequential findings in the history of science. Distant galaxies, he showed, were moving away from Earth, and the farther they were, the faster they were receding. The relationship was clean. Recession speed was proportional to distance. A galaxy twice as far away was receding twice as fast. The natural interpretation was that the universe was expanding, and that interpretation was correct. But the expansion is not what it first appears to be. Galaxies are not flying through space away from us, like fragments from an explosion. They are not moving through space in the way a thrown ball moves through air. Space itself is expanding. The fabric of the universe, the medium in which distance is measured and through which light travels, is stretching. New space is being continuously created between every pair of points in the universe. The galaxies are, locally, roughly stationary in their own neighborhoods. It is the space between neighborhoods that is growing. The rate of this expansion is quantified by a number called the Hubble constant. Its precise value is the subject of ongoing scientific debate. Different measurement methods produce slightly inconsistent results, a discrepancy known as the Hubble tension that remains unresolved, but estimates cluster around 67 to 73 kilometers per second per megaparsec. 1 megaparsec is about 26 million light-years. So for every 26 million light-years of distance between two objects, the space between them is growing at about 70 kilometers per second. At short distances, this is irrelevant. The expansion is completely overwhelmed by local gravity. Our solar system is gravitationally bound. The Milky Way is gravitationally bound. The local group, the cluster of a few dozen galaxies that includes the Milky Way, Andromeda, and their satellite galaxies, is gravitationally bound. The expansion has no practical effect on any of these scales. It only begins to dominate over distances where gravitational attraction between galaxy clusters becomes weaker than the cumulative expansion of the space between them. But at large enough distances, a remarkable thing happens. There is a distance at which the expansion of space between us and a distant object is occurring fast enough that the expansion velocity exceeds the speed of light. Not because anything is moving through space faster than light, that remains impossible, but because space itself is not bound by the light speed limit. Space is not a thing traveling through space. It is the substrate, and the rate at which it is created between two distant points can, and does, exceed the rate at which light can travel across the gap. This critical distance where the recession velocity equals the speed of light is called the Hubble radius. It currently sits at approximately 4 billion light-years from Earth. Beyond the Hubble radius, any object is currently receding from us faster than light can cross the intervening space. A photon emitted by an object beyond the Hubble radius and aimed toward us will make progress. It will move through its local space toward us at the speed of light. But the space between us and the photon is expanding faster than the photon can traverse it. The gap grows. The photon never arrives. This defines an unreachable region, not a distant region, not a distant region, not a hard-to-reach region, a region from which nothing, no light, no signal, no message, no spacecraft, can ever reach us, not in any future time, not with any technology. The physics is absolute. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, extends about 5 billion light-years in every direction. That is larger than the Hubble radius because the universe was smaller in the past, and light that is now reaching us began its journey when the distances involved were smaller. but much of what we can currently observe has already crossed our cosmic event horizon. It is receding from us faster than light, and while light it emitted in the past is still reaching us, it is the last light that ever will. Those galaxies are, in a specific and precise sense, already gone from our future. In 1998, two independent teams of astronomers, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory, the other by Brian Schmidt and Adam Rice at Harvard, announced that distant Type Ia supernovae were dimmer than expected. The only explanation consistent with the data was that the expansion of the universe was accelerating, not slowing down as had been assumed, accelerating. Something is driving the expansion faster over time. That something has been named dark energy, and while we can measure its effects with precision, its fundamental nature remains one of the deepest open questions in physics. Perlmutter, Schmidt, and Rice shared the Nobel Prize in Physics in 2011 for this discovery. The accelerating expansion means that the cosmic event horizon is effectively shrinking. More and more of the universe is being permanently lost to us as the expansion accelerates. Galaxies that are currently just barely within our observable universe will eventually be pushed beyond the event horizon. Their light will redshift to longer and longer wavelengths, growing dimmer and dimmer, until it fades beyond detection entirely. In the far future, on timescales of trillions of years, the Milky Way and its gravitationally bound companions will be alone in a universe that appears, to observers within it, to contain nothing else. All other galaxies will have retreated beyond the horizon of visibility. We are, it turns out, living in a relatively good era for cosmology. The universe is young enough that there is still a great deal to observe. In 1 trillion years, the view from any surviving civilization would be dramatically impoverished. For the question of interstellar and intergalactic travel, the expanding universe adds a constraint that operates independently of the energy wall and time dilation. Even if a civilization solved both of those problems, even if they found a way to travel at an arbitrarily large fraction of the speed of light without the energy costs, some destinations would remain permanently, geometrically unreachable, not because of any difficulty in reaching them, because the space between them and us is growing faster than anything can cross. The cage is not just made of fuel requirements and relativistic time costs, it has sealed walls at the edges, walls that are moving outward, walls beyond which nothing is coming and nothing can go. The discovery of the accelerating expansion was not something anyone expected. Before 1998, the standard assumption in cosmology was that the expansion of the universe was slowing down. This was logical. The universe contains matter. Matter has gravitational attraction, and gravity should be pulling everything back together, decelerating the expansion over time. The question was how much deceleration, and whether it would eventually halt and reverse into a collapse. The two teams studying distant supernovae were trying to measure that deceleration. Type Ia supernovae, produced by specific stellar explosions that occur at a consistent intrinsic brightness, can be used as standard candles because their true brightness is known. Measuring their apparent brightness tells you their distance. Measuring their redshift tells you their recession velocity. Together, distance and velocity across different cosmic epochs reveal the history of the expansion. Both teams found the distant supernovae dimmer than expected, not slightly, enough to require a fundamental revision. If the expansion were decelerating, distant supernovae would be closer than they appear in a uniformly expanding universe. Because in a decelerating universe, there was less expansion in the past, and the objects are not as far as a naive calculation suggests, but the supernovae were farther than expected, meaning they were less bright than expected. The expansion was not decelerating, it was accelerating. Something was pushing the universe apart, and that push was growing more powerful over time, not less. The something was named dark energy. What it actually is remains one of the deepest unsolved problems in physics. The simplest mathematical description is a cosmological constant, a term in Einstein's field equations that Einstein himself introduced and later abandoned. The constant represents a form of energy inherent to empty space, constant throughout the universe and over time. Whether this description is physically correct or merely a mathematical convenience that happens to fit the data is unknown. Dark energy currently comprises approximately 68% of the total energy content of the universe. Dark matter, which influences the gravitational dynamics of galaxies and clusters but does not interact with light, comprises approximately 27%. Ordinary matter, everything we can see and touch and build from, comprises approximately 5%. We live, it appears, in a universe 95% of whose content we do not understand, and the 68% we call dark energy is what is accelerating the expansion, sealing off more and more of the universe behind the event horizon, ensuring that the observable universe we inhabit will become less and less connected to the rest of existence over time. The cage is not static, it is actively closing. Find a dark night. Step outside. Look up. What you are seeing is not the universe as it is. It is not even close to the universe as it is. What you are seeing is a composite, a mosaic assembled from light that left its sources at different points across billions of years of cosmic history, all arriving at your eyes simultaneously on this particular evening, because the physics of light travel time happens to place all those different signals at your location at this moment. The sky you see is not a single snapshot. It is thousands of photographs taken at different times, printed on the same page. The moon is 1-3 light seconds away. You see it as it was 1-3 seconds ago. Venus, depending on its position in its orbit, is anywhere from 2 to 14 light minutes distant. The Sun is 8 minutes away. Mars, at closest approach, is about 3 light minutes. Jupiter, roughly 40 light minutes. Saturn, a bit over an hour. These are all inside our solar system. Now look at the fixed stars. Alpha Centauri, our nearest stellar neighbor, visible from the southern hemisphere, is 424 light-years away. The light you see left it when a child currently in primary school was just being born. Sirius, the brightest star in the night sky, is 6 light-years distant. Polaris, the North Star, used for navigation for thousands of years, is roughly 430 light-years away. The light reaching your eyes from Polaris tonight departed around 1595 CE, during the reign of Elizabeth I of England. Deneb, one of the brightest stars in the northern summer sky, is estimated at approximately 2600 light-years away. The light arriving from Deneb tonight left its source around 600 BCE, before Socrates was born, before Plato, before the building of the Parthenon. Before much of what Western civilization would call its intellectual foundation existed, the Orion Nebula, that fuzzy patch in the Sword of Orion, visible to the naked eye on a good night, is about 1,344 light-years away. The light from it currently reaching us left its source around 680 ACE during the early medieval period. The Andromeda galaxy, faintly visible to the naked eye as an elongated smear in a dark sky, is 537 million light-years distant. The light arriving from Andromeda tonight left its source before the genus Homo existed, before Homo erectus, before the last common ancestor of Neanderthals and modern humans walked the Earth. You are looking at a galaxy as it appeared in the Pliocene epoch, when the ancestors of humanity were small-brained hominins walking the savannas of East Africa, and the light from the most distant objects visible to powerful telescopes left its source when the universe was less than 1 billion years old, when the first galaxies were still forming, when stars were being born in conditions that no longer exist anywhere in the universe. All of this light is arriving now. Simultaneously, in one evening of observation you can receive signals from 1 billion years of cosmic history, all at once, layered across the sky by the accident of their distances from Earth. But here is the part that quietly changes how the sky feels. Some of the stars you see tonight do not exist anymore. A star 1,000 light-years away that you observed tonight existed 1,000 years ago. Whether it still burns, whether it has not, in the intervening millennium, exhausted its fuel, collapsed into a white dwarf, or exploded into a supernova, is information that has not yet arrived. If that star exploded 900 years ago, the news is still 100 years away from reaching us. At some point in the future, perhaps centuries from now, perhaps sooner, a bright new light will appear in the sky visible, perhaps even in daylight, and it will be the first moment anyone on Earth learns what has already been over for 1,000 years. You can see something that no longer exists. You can observe a stellar object that burned out before your great-great-great-grandmother was born and still see its light as though it were real. It is real. The light is real. The Southernite is real. The star that produced it may not be. Betelgeuse, the distinctly reddish star in Orion's shoulder, is estimated at somewhere between 500 and 700 light-years distant. It is a red supergiant nearing the end of its life, and it will at some point explode in a supernova, briefly becoming bright enough to be visible in daylight and cast shadows at night. Astronomers cannot predict exactly when. It could be in 10,000 years. It could be in 100,000 years. Or, and this is the part that takes a moment to absorb, it could have already happened. If Betelgeuse exploded 400 years ago, that news will not reach us for another century or more. We would be watching a star that has already exploded, seeing it glow steadily, entirely unaware. This is not a thought experiment. This is the literal condition of observation in a universe where light travels at a finite speed. The night sky is an archive. Every point of light is a data point from a different era. Some of those eras ended long ago. The sky is full of records of things that no longer exist, and full of things that currently exist but have not yet had time to be seen. Because the light has not yet arrived, the present is hidden from us. The past is all we have access to. This is the universe that any civilization, here or elsewhere, inhabits. Not just us. Any mind, anywhere, looking out from its own position, sees the same structure, light from its past, silence about its present, uncertainty about everything beyond its event horizon. The archive is universal. The isolation it creates is universal. And into this universe, Enrico Fermi asked a question that has not been answered. The Los Alamos National Laboratory in the summer of 1950 was not a quiet place. It was the post-war home of the Manhattan Project's scientific community, a high-desert facility in New Mexico, perched on a mesa populated by some of the most accomplished physicists in the world. The conversations at lunch were not small talk. They ranged across nuclear physics, cosmology, mathematics, philosophy, and the state of the world that the wartime project had permanently changed. Enrico Fermi was there. He was Italian-born, a Nobel laureate in physics, and widely regarded as one of the most versatile scientists of the 20th century. Equally comfortable designing experiments and deriving theory, capable of working across fields in ways that few could match. He had designed the first artificial nuclear reactor and built it under a sports stadium in Chicago in 1940. He had worked on the bomb. He was, by any measure, one of the most consequential physicists alive. During a lunchtime conversation about extraterrestrial life, apparently prompted in part by a newspaper cartoon about aliens stealing trash cans, Fermi listened to the discussion and then asked a question. Where is everybody? The question was simple. The implications were not. The logic behind it is easy to reconstruct. The galaxy is 100,000 light-years across. It contains somewhere between 100 billion and 400 billion and 400 billion stars. A number so large it resists intuition. A substantial fraction of those stars are thought to be orbited by planets. A fraction of those planets presumably exist in conditions where complex chemistry is possible. Given the age of the galaxy, roughly 6 billion years, there has been enormous time for life, and potentially intelligence, to arise somewhere. If any civilization has arisen with even a modest head start on us, say 1 million years, and if it developed the capacity for interstellar travel in any form, even slow colonization ships moving at small fractions of the speed of light, it would have had time to spread across the entire galaxy many times over. A civilization moving at 1% of the speed of light, colonizing nearby star systems and sending new ships outward from each colony, could in principle fill the Milky Way in roughly 10 million years. The galaxy has been around for 13.6 billion years. 10 million years has had 1,360 opportunities to happen. So where are they? No signals of undeniably artificial origin have been received. No megastructures, the kind of large-scale engineering that a sufficiently advanced civilization would logically build around a star, have been detected in astronomical surveys. No artifacts have been found in our solar system. No evidence of intelligent manipulation of the galactic environment at any scale has been identified. The search for extraterrestrial intelligence has been conducted in various forms since the early 1960s. Frank Drake, the astronomer who in 1961 formalized the question in what became known as the Drake equation, conducted the first systematic radio search in 1960, pointing a radio telescope at two nearby sun-like stars and listening for signals. Generations of researchers have followed, using increasingly sensitive instruments, scanning wider areas of sky, looking in more frequency ranges. The Drake equation itself is not a calculation so much as a framework, a structured way of thinking about the variables that determine how many communicating civilizations might exist in the galaxy at any given time. It multiplies together factors including the rate of star formation, the fraction of stars with planets, the fraction of those with habitable conditions, the fraction where life arises, the fraction where intelligence arises, the fraction that develops detectable technology, and the average lifespan of such civilizations. The equation can produce any number from almost 0 to millions, depending on the values assigned to the unknown factors. The silence has generated many proposed explanations. The Great Filter hypothesis, developed by economist Robin Hanson in 1998, suggests that somewhere in the chain from simple chemistry to space colonizing civilization, there exists a barrier so difficult to cross that almost no lineage succeeds. The unsettling version is that the filter lies ahead of us, in some challenge or catastrophe that advanced civilizations inevitably face and almost universally fail to survive. The slightly less unsettling version is that the filter is behind us, that some step we have already passed, such as the origin of life, or the emergence of eukaryotic cells, or the development of intelligence itself, was so improbable that it essentially never happens anywhere else. In this version, we are genuinely rare, possibly unique. Other explanations propose that civilizations destroy themselves before achieving interstellar reach, or that they transition to some mode of existence, perhaps digital, perhaps non-physical, that doesn't produce the kind of electromagnetic signals we are listening for, or that the universe is genuinely young enough in terms of the conditions for complex life that very few civilizations exist yet, or that civilizations do exist and have detected us but have chosen not to signal their presence. What the physics described in this conversation adds to the Fermi paradox is not a solution but a constraint. The energy wall is real, and it is the same everywhere. Any civilization must pay the same energetic toll for interstellar travel. The Tsiolkovsky rocket equation, the mass-energy relationship, conservation of momentum, these are not Earth-specific, they are universal physics. The time dilation exile is real, and it is the same everywhere. Any crew that achieves relativistic speeds departs irreversibly from the civilization that sent them. This creates a genuine civilizational disincentive to send anything that includes beings who will lose their connection to home. The cosmic event horizon is real, and it is the same everywhere. Some regions of the universe are permanently inaccessible to every civilization simultaneously. This is not a local feature of our particular location. The expansion affects every point in the universe equally. The silence, in this light, becomes not so surprising. Not explained, the Fermi paradox remains genuinely unresolved, and the honest answer to where everybody is remains that we do not know. But the silence becomes more consistent with a universe that has made interstellar travel extraordinarily expensive, exile-inducing, and, at large enough scales, geometrically impossible regardless of technology level. The galaxy may not be empty, it may be occupied here and there in ways we have not yet detected. But if it is occupied, those civilizations are contending with the same physics we are, the same distances, the same energy requirements, the same expanding geometry, the same fundamental constraints. And they are, as far as we can tell, as silent as the distances and physics would lead us to expect them to be. We have been treating the speed of light as a speed limit throughout this conversation, a posted rule, a constraint imposed by physics on the things inside it, the way a traffic law is imposed by society on the people inside it, as though someone set the limit and something might eventually find a way around it, through cleverness, through new physics, through some loophole that the rule makers overlooked. That framing is wrong, and the correct framing is stranger than any loophole. The speed of light is not a limit imposed on things that move. It is the structure of space-time itself. To understand why, it helps to trace what the speed of light actually is, in the deepest physical sense. In 1865, the Scottish physicist James Clerk Maxwell unified the previously separate theories of electricity and magnetism into a single coherent framework. Maxwell's equations, 4 equations that describe how electric and magnetic fields are generated, interact and propagate, predicted that these fields could travel through empty space as waves. When Maxwell calculated the speed at which electromagnetic waves would propagate, using the fundamental constants of electrostatics and magnetostatics that had been measured in laboratory experiments, he obtained a number, approximately 310,000 kilometers per second. He recognized immediately that this matched, within experimental precision, the measured speed of light. The conclusion was clear. Light is an electromagnetic wave, and its speed is not a property of light specifically, it is a property of the electromagnetic field, which means it is a property of empty space itself, the permittivity and permeability of free space, 2 fundamental constants describing how electric and magnetic fields behave in vacuum, together determine the speed of light. The speed of light is set by the geometry of empty space. This was already remarkable. Then Einstein went further. Einstein's special relativity reveals that space and time are not 2 separate things. They are aspects of a single unified structure, space-time. The geometry of space-time, the way distances in space and intervals of time are related, is built around a fundamental constant that plays the role of a conversion factor between spatial distances and temporal ones. That constant is the speed of light. The famous equation E equals mc squared is a direct expression of this. The c in the equation is the speed of light, but it appears not because the equation is specifically about light. It appears because c is the conversion factor between mass and energy, just as it is the conversion factor between meters and seconds in space-time geometry. The speed of light is the number that makes space-time geometry consistent. It is woven into the structure at the most fundamental level. Now consider what it would mean to exceed it. In special relativity, whether one event can causally influence another depends on whether a signal traveling at or below the speed of light can travel between them. This defines what physicists call the light cone, a conceptual structure that for any given event divides spacetime into 3 regions: the past, which can influence the event, the future, which the event can influence, and the space-like separated region, which is neither before nor after in any observer-independent sense, and which cannot exchange causal signals with the event. Faster-than-light travel would allow a traveler to move outside their own light cone, and because the light cone structure of spacetime is the same from any reference frame, this is one of the deep results of special relativity. Moving outside your light cone in one frame means, in some other perfectly valid inertial frame, arriving at the destination before you departed. This is not a problem of definition, it is a causal paradox. If you can arrive before you leave, you can potentially encounter yourself before you have made the decision to travel. You can send a message to your past self. You can arrange for effects to precede their causes. The chain of cause and effect, which is the conceptual foundation on which all of physics, all of science, and arguably all coherent reasoning rests, breaks down. A universe that permitted faster-than-light travel would also permit closed causal loops, events that cause themselves, effects that exist without causes. The chain of explanation, this happened because that happened, loses its meaning, not in some abstract philosophical sense. In the specific, mathematical, experimentally verified framework of spacetime physics, the speed of light is not fast. It is not slow. Speed is a comparison, and the speed of light is not best understood as a comparison with anything. It is better understood as the conversion rate between space and time, the ratio at which distance and duration trade off against each other in the geometry of spacetime. It is the number that makes before and after mean something consistent across all reference frames. Nothing can exceed it, not because a rule forbids it, but because exceeding it would require a universe with a different logical structure, a universe in which causality, the directional flow of cause and effect, no longer holds. Such a universe might exist somewhere in logical possibility space, but it would not be this universe. It would have different physics at the deepest level, different geometry, a different relationship between the things that happen and the things that explain them. The cage is not technological. It is not political. It is not even purely physical in the everyday sense. It is logical. It is built into the structure of the universe at the level where physics and mathematics meet, where the equations that describe space-time would have to be different equations in a universe without the constraint. Any civilization, anywhere, any age, any level of development, lives inside this constraint, not a version of it, not an approximation of it. This constraint with these specific numbers derived from these specific structures of space-time geometry, they cannot exceed the speed of light for the same reason we cannot. Because the speed of light is not a rule that applies to them from outside. It is the structure they exist inside, and knowing that, the question of what the equations allow, even within the constraint, becomes interesting. Physicists are not people who accept a cage without examining every bar, every joint, every weld. For over a century since Einstein handed the world the frameworks of special and general relativity, theoretical physicists have been doing exactly this, methodically searching the mathematics for structures that might allow something that looks like faster than light travel, or at least functions like it without technically violating the laws as stated. They are not doing this naively or optimistically necessarily. They are doing it because the equations are there, the solutions are there. And you cannot claim to understand what a theory forbids without first exhausting what it permits. 3 candidates have emerged. All 3 are real mathematical structures within verified physics. All 3 have problems that no one has solved. The first is wormholes. In 1935, Albert Einstein and his colleague Nathan Rosen were studying the mathematical properties of black hole solutions to the equations of general relativity. A black hole is a region of space-time where the curvature becomes extreme, so extreme that the escape velocity at a certain radius exceeds the speed of light, trapping everything inside. The mathematics describing a black hole is known as the Schwarzschild metric. When Einstein and Rosen examined what the mathematics said about the geometry on the other side of a black hole's singularity, they found something unexpected. The equations described a bridge, a tunnel connecting 2 separate regions of space-time, each looking from the inside like a black hole opening. The structure is now called an Einstein-Rosen bridge. Later theoretical work, particularly by Kip Thorne and colleagues at Caltech in the 1980s and 1990s, explored whether such a structure could be made traversable, whether a traveler could actually pass through it. The mathematics said yes in principle, with one requirement. The wormhole's throat would need to be threaded with exotic matter, matter with negative energy density, meaning matter that is less energetic than empty space. Negative energy density sounds impossible, but is not entirely absent from known physics. The Casimir effect demonstrates that the vacuum between 2 closely spaced metal plates has lower energy than ordinary vacuum, negative energy density in a localized region. This is real. It is measured. The effect is small, observable only at separations of micrometers or less, and the total negative energy involved is vanishingly tiny. Whether exotic matter with a negative energy density can exist in quantities sufficient to stabilize a macroscopic wormhole, one large enough for a spacecraft to pass through, is not known. Physics does not clearly forbid it. Physics does not offer any mechanism for producing it. The theoretical gap between the Casimir effect and a traversable wormhole is, at minimum, enormous, and some theoretical work suggests that any realistic wormhole would be inherently unstable, collapsing faster than any signal could traverse it. The wormhole is a real solution to real equations. It has never been observed. There is no known mechanism for creating or stabilizing one. The second candidate is the Alcubierre drive. In 1994, Miguel Alcubierre, then a physics PhD student at the University of Wales, published a paper in the journal Classical and Quantum Gravity. The paper described a metric, a solution to Einstein's field equations, in which a region of space could move faster than the speed of light without violating special relativity locally. The mechanism involved contracting space ahead of a bubble and expanding it behind. Inside the bubble, space-time is locally flat. The ship inside experiences no acceleration, no unusual gravitational field, no time dilation relative to an external observer. The bubble itself and everything inside it moves as a unit. This is technically consistent with special relativity because no local motion within the bubble exceeds the speed of light. The motion is a property of spacetime geometry, not of the ship through spacetime. The paper was received as a genuine contribution. It was physically creative and mathematically rigorous. The concept does not obviously violate any law of physics as currently understood. The problems are also genuine. Alcubierre's original calculation required an amount of exotic matter with negative energy comparable to the mass energy of Jupiter. This is not a barrier on the scale of engineering difficulty. It is a barrier on the scale of physics. There is no known mechanism for producing or concentrating negative energy at that scale. Harold White at NASA's Johnson Space Center published work in 2012 proposing modifications to the bubble geometry that could reduce the energy requirement by many orders of magnitude, potentially to quantities still large but not planetary. These refinements sparked interest. They also sparked careful criticism. The debate about whether the revised calculations are physically consistent remains ongoing among specialists. Additionally, the interior of an Alcubierre bubble is causally isolated from the bubble's leading edge. The crew inside cannot send signals to the front of the bubble. Those signals would need to travel faster than the bubble itself to reach the leading edge. This means the crew cannot steer, cannot respond to obstacles, cannot interact in any way with what lies ahead. Building a propulsion system that the crew cannot control is an unsolved engineering problem of a specific and strange kind. The third candidate is quantum entanglement. Quantum entanglement is not theoretical. It is one of the most thoroughly confirmed phenomena in all of modern physics. When two particles are prepared in an entangled state, their quantum properties correlated through a specific interaction. Measurements performed on one particle are found to be statistically correlated with measurements performed on the other, regardless of the distance between them. The correlation appears instantaneous in every experiment that has tested it across distances ranging from meters to kilometers. John Bell, working in 1964, derived inequalities that any locally realistic theory, any theory where correlations are explained by shared information traveling at finite speeds, must satisfy. Experiments beginning in the 1970s and continuing with increasing precision through the 2010s have consistently violated Bell's inequalities. The correlations are real and cannot be explained by any pre-existing shared information. Something non-local is happening, but the no communication theorem, which follows directly from the mathematics of quantum mechanics, proves that this non-locality cannot be used to transmit information. The outcome of any measurement on one entangled particle is random, genuinely random, in a way that is not merely uncertain but fundamentally unpredictable. Only after comparing both sets of measurement results through ordinary light-speed limited classical communication do the correlations become apparent. Without that classical channel, neither party can extract any information from the measurement outcomes alone. The randomness conceals the correlation until the two records are compared. Entanglement is real. The correlations are real. Information cannot travel through them faster than light. The no communication theorem holds. 3 scenes. 3 places where the mathematics of known physics touches something that looks like faster than light capability. Wormholes, real solution, no known construction mechanism, no stability mechanism, requires exotic matter not known to exist at useful scales. Alcubierre drive, real metric, requires exotic matter, causally isolated interior, engineering control problems not resolved. Quantum entanglement, real correlations, provably cannot transmit information. Every bar has been checked, none of them open. The cage has genuinely interesting interior structure. It has mathematical passages that connect unexpected places. It is not featureless, but it does not have a door. And this, strangely, is not the end of the story. The end of the story involves the fact that the cage itself makes remarkable. A fact about what the cage contains. We began with a title that, at first glance, sounds like a complaint. The speed of light is so slow that aliens may never make it to Earth. Having spent all this time in the physics, it is worth being precise about what was actually found. The speed of light is not slow, not in any ordinary sense of the word. It moves at 299,790 kilometers per second. It circles the equator of Earth 7 times per second. It crosses the Moon's distance in 1/3 seconds. It illuminates the room you are sitting in less time than a single synapse can fire. By any everyday measure, by any comparison that exists on the surface of a planet, it is the fastest thing there is. What is slow is not the speed. What is slow relative to the universe is everything. The universe is built at a scale where even that speed, the maximum speed that physics permits, the rate at which causality itself propagates, takes 424 years to cross the gap to the nearest star, 5 million years to cross to the next large galaxy, and somewhere in the range of 46 billion light-years to reach the current edge of the observable sphere, and beyond that edge lies an unknown volume of the universe, possibly infinite, almost certainly far larger than what we can see, from which no signal will ever reach us, and to which no signal from us will ever travel. The speed is not the problem. The architecture is. And into this architecture, any civilization that exists anywhere faces the same set of walls. The energy wall, the exponentially increasing energetic cost of accelerating mass to significant fractions of light speed. Real, derived from conservation of momentum, universal. The exile problem, the time dilation that makes fast travel a one-way departure into a future civilization that did not know the traveler. Real, measured, universal. The sealed regions, the cosmic event horizon beyond which the expansion of space permanently disconnects the universe from itself. Real, confirmed by supernova observations, universal. The walls do not bend for intelligence or ambition or longevity. A civilization a billion years ahead of us in development lives in the same spacetime, uses the same Tsiolkovsky equation, answers to the same Lorentz vector, confronts the same Hubble constant. Physics is not local constant. Physics is not local. It does not adjust for species. So what does this mean for the silence? It might mean very little beyond physics. The Fermi paradox remains genuinely open. The honest answer to whether other civilizations exist is still that we do not know. The honest answer to whether they could reach us, given enough time and development, is complicated by the walls described here, but not definitively answered. Some paths through the cage might exist that current physics has not found. The seams in the cage are real. A future physics might find ways through them that current physics cannot. Wormholes and Alcubierre metrics are not nothing. They are genuine structures in verified equations. The honest answer is, we do not know. What we do know is the geometry, the speed, the cost of approaching it, what it does to time, the expansion, the event horizon, the sealed zones, the mathematical seams and why they do not currently open, and knowing all of that, lying here at whatever hour this finds you, with whatever version of night is outside your window, there is one thing that seems worth sitting with before sleep. Not the distances, not the cage, not even the silence. The fact that something inside the cage is looking out. The universe produced, somewhere inside this vast constrained geometry, minds capable of measuring their own isolation, capable of deriving the equations that describe their confinement, capable of understanding, in precise mathematical terms, exactly how sealed the structure is, and of finding that understanding interesting rather than simply defeating. That is the unexpected thing, not the walls. The response to the walls, something inside an apparently isolated cosmic bubble on a small planet around an ordinary star in an unremarkable spiral galaxy, worked out the Lorentz vector, measured the Hubble constant, found the seams in the cage, checked every bar, and then, having confirmed that the bar's hold looked up anyway, kept looking, kept calculating, kept wondering what is out there, even knowing that out there is, by the physics derived in this conversation, effectively unreachable. That decision, to look, to measure, to ask, despite the answers, may be the most remarkable thing in the observable universe. Not the distances, not the speeds. The fact that something with a lifespan of decades, made of atoms that will disperse into ordinary matter long before any interstellar journey could complete, chose to sit with the scale of what it cannot reach, and did not look away. The rest of the night is yours. There is one more thing worth naming, something the physics tends to obscure because the physics is so large. Every number in this conversation was worked out by a specific person, at a specific time in a specific time, in a specific place. Ole Rømer at a telescope in Paris in 1676 watching a moon of Jupiter and noticing that the numbers did not add up, with no expectation that his anomaly would eventually teach the world about the finite speed of light. James Clerk Maxwell in his study in Scotland, writing equations for fields he had never seen directly. Equations that turned out to contain the speed of light as a hidden constant. Albert Einstein at a patent desk in Bern, deriving from two postulates a description of spacetime that more than a century of experiments has failed to contradict. Edwin Hubble at the eyepiece of a 100-inch telescope on a California mountaintop, measuring the recession of distant objects and finding that the universe was larger than almost anyone had believed possible. Saul Perlmutter and Brian Schmidt and Adam Rice, analyzing supernovae from opposite ends of the planet and arriving independently at the same unwelcome conclusion: the expansion is not slowing, it is accelerating. These were all acts of looking. Sustained, careful, patient, sometimes obsessive acts of looking at a universe that does not require being looked at or understood. The distances are what they are whether or not any mind calculates them. The Hubble constant operates whether or not any civilization measures it. The light cones exist whether or not any being traces their geometry. And yet, something inside the cage insisted on knowing, found out how large the cage is, found out what the bars are made of, found out that the bars are made of logic, not material, and that the cage has seams but no door, and continued looking. That is the thing worth carrying into sleep tonight, not the cage, the looking.